Hello, in this video we're going to be talking about center of mass or centroid. The center of mass or centroid is a point that the object would balance on. So as you probably know from playing on a seesaw or teeter-totter as a child, if two children of unequal weights are on the equipment, then we can balance by placing the heavier child near the fulcrum and the lighter child further away. So we're interested in not only the weights or masses, but also how far away they are from the fulcrum. This is going to lead us to a method of finding where to place that fulcrum to balance it. So first of all, let's look at what are called point masses on a number line. So point mass is basically just a point. We're going to assign a weight to it, and we have that. So suppose we have a number line of no weight, and we place it on it point masses. Okay. So if we multiply the mass of the points by their coordinates and add them together, then we obtain what we call the first moment about the y-axis, the first moment about the x equals 0. This is the tendency for the line to rotate about the y-axis. If we then divide this sum of the masses by the sum of the masses, then we obtain a weighted average of the point masses. This is exactly what we have when we find the arithmetic mean or average of these locations weighted by their masses. The result will be the center of mass or centroid of the point masses. This would be the location to place the fulcrum so that the system would balance perfectly, a balance point. So let's look at this example here where we have some masses, and here we have some points placed at -6, 1, 2, 8, and 10 on a number line on the x-axis, and they have masses of 1, 2, 2, 5, and 3 respectively. If you add up those masses, you get 13. If we multiply 6 times 1, we get -6. 1 times 2 is 2. 2 times 2 is 4. 8 times 5 is 40. 10 times 3 is 30. And then we sum up those masses times their x-coordinates, we get 70. Divide 70 by 13, we find the centroid. So there is the moment about y is the 70. And then the mass, total mass, was just adding those up. That's 13. And dividing the two, we get 70 13s, or 5.384615, with the 384615 being a 6-digit repeating pattern. And that is the x bar, we call it, x, the little line over it, x bar, which is the mean or centroid, or the x-coordinate of that, the center of mass. So here you can see the points. I've got one at -6, a little heavier point. That one's weight 1. We have two masses of weight 2 at 1 and 2. I've made the dots a little bigger and put the numbers above so you can see that. A little bit bigger, heavier mass at 3. The heaviest one is mass 5, and it's at 8. So the mass of 3 is at 10. And we see that the balance point is right here. It's approximately 5.38, and that's the balance point where that would balance perfectly. So of course that's a discrete example, so there is no calculus involved. Now let's look at a more continuous example, so we'll need some calculus. We want to find the centroid of a rod that's along the x-axis. So in the following example, we generalize this concept, applying it to a rod lying along the x-axis with the symmetry in the y and z directions, but variable density along the x-axis. The rod goes from x equals a to x equals b, and its density, that's a mass per length, because the other cross sections are the same, is given by rho of x. As usual, the idea is to chop up the rod into little pieces of width delta x, approximate each of those pieces as if it were a point mass, find the center of this set of point masses using the same technique as above. We then take a limit as the number of pieces goes to infinity, and their widths approach 0 to get a definite integral. So the mass then becomes the integral from a to b of rho of x dx. The moment about y is the integral from a to b of x times rho of x dx. The x bar is is the moment about y divided by the mass. If you remember from probability, this is basically how we found the mean was x times the PDF of x. The total mass, the total probability is 1, so we're just dividing by 1. So we found x bar, or mu, the mean, to be just x times that probability density. Okay, so this is a very similar situation. So the center of mass of a rod is the point at which you would place a pivot so that the rod balances. To find the position of the center of mass of the rod, you first calculate its moment, then divide the moment by the total mass. Find the center of mass of a rod in question 26. Well, back in question 26 from the previous video, we had a rod of varying density. It was 0 at one end and 10 at the other end on x-axis. The density was given by rho of x equals 10 times sine of pi x over 10. And find the mass of the rod. Maybe I should go ahead and call that a linear density, because it's a mass per linear unit. Okay, find the mass of the rod. Okay, well, we did that earlier. It's just integrating the density function from 0 to 10. The details are worked out here, but it's 200 over pi, or approximately 63.66. The moment about y is just take the same density function, but multiply that by x and integrate that over the length of the rod. This one you have to use integration by parts. I'll let you supply the details of that integration yourself, but here's the antiderivative. 100 over pi times the opposite of x times cosine of pi x over 10 plus 10 over pi times sine of pi x over 10. So it's a pretty straightforward integration by parts and then substitution integral. We're going to evaluate that antiderivative from 0 to 10. Let's see, plug in 0. That's 0 because of the x. This is 0 because sine of 0, 0. This gives you sine of pi, which is also 0. This gives you cosine of pi, which is -1. And then, so that makes this positive x. X is 10, so this is 10 times 10 is 1,000 over pi. All right, so it's the moment about y is 1,000 over pi. The center of mass is take that moment about y and divide it by the mass. So when you flip this guy over and multiply, the pi's cancel. You get 1,000 over 200, and that reduces to 5. So the centroid is at 5 on the x-axis, 5, 0. This is a kind of strange rod because it does reach 0 density at some times, which would be kind of weird. But anyway, the basic idea works fine. Now let's generalize it to 2 dimensions. So we can generalize the point mass situation to 2 dimensions by letting the points be anywhere in the xy plane. The total mass of the system is again found by adding up the masses of the individual points. The moment about the y-axis, m sub y, is again found by multiplying the x-coordinates of the points by their masses and summing. We once again divide the moment about the y-axis by the total mass to find x bar, the x-coordinate of the centroid. Similarly, the moment about the x-axis, m sub x, is found by multiplying the y-coordinates of the points by their masses and summing. We divide the moment about the x-axis by the total mass to find y bar, the y-coordinate of the centroid. So m is just the sum of all your individual point masses, of all those masses. M sub y is multiply the x value times the m, add those up. M sub x is multiply the y values of each point times its mass and add them up. And then you just divide to find x bar and y bar. So here's an example. Here we have, say, 5 points, and we have their corresponding masses here. Summing those masses, we get 20. And here we take the x-coordinate and multiply to get you this times the mass to get you this column. So -2 times 2 is 4, -4. 3 times 1 is 3, 2 times 3 is 6, 4 times 5 is 20, -5 times 6 is -30. Sum those to get -5, and that is the m sub y. which is used to find x bar. Divide that by 20, you'll get x bar. Similarly, we do the same thing for the y coordinates. 3 times negative 4 3 times 2 is 6. Negative 5 times 1 is negative 5. 1 times 3 is 3. 6 times 5 is 30. And the y here times the mass here, negative 4 times 6 is negative 24. Add those up, we get positive 10. That's the moment about the x-axis, which is used to find y bar, by dividing it by the mass of 20. So the mass is 20, m sub y is negative 5, m sub x is 10. Do a little dividing. Negative 5 over 20 is negative 1/4, or negative 0.25 for x bar. And y bar is 10 over 20, which is 1/2, or 0.5. All right, so now we want to further generalize the idea to finding the center of mass for what we call a planar lamina. Planar lamina can be thought of as a region in the plane with a very thin thickness in the third dimension. It will have a mass, it might be an irregular shape, and it might have a density that varies throughout the region. Therefore, it will require calculus to compute its center of mass. Sometimes symmetry can help calculate centroids, but only if the region and its density both have symmetry. The more general case requires use of functions of two variables, so we will revisit this idea in Calculus 3. However, if we can get everything as a function of one variable, say x, then we can use a single variable integral calculus to find the centroid. We'll do that now. Here's how this works. Let's assume that we have some region in the xy plane whose boundaries can be described by functions of x. Let's say above it's bounded by f of x and below by g of x. On the left and right by x equals a and x equals b, respectively. And as usual, what we want to do is divide it up into small pieces. We want to get everything in terms of the single variable x, so we divide it up into vertical strips of width delta x. We approximate each of these strips with a rectangle. So for this to work, we need the density of the strip to be constant on the strip, so it depends only on the value of x. If that's not true, then see the Calculus 3 technique. We multiply the density, mass per area, on the strip by the area of the strip to obtain a mass for the strip. Of course, the area of the strip is just basically length times width, because it's a rectangle. We add these up to get an approximation of the mass of the lamina. As usual, we'll take the limit as the number of strips goes to infinity and their widths go to 0 to produce an integral giving the mass of the lamina. So it's just top curve minus bottom curve is the length of the strip, times dx, its width, will give you an area, times rho, which is a mass per area, will give you a mass and then we integrate all that up. We find the moment about y in a similar manner, slice it up as we would to find the mass, but we're integrating x times the integrand used to find the mass. We again divide the moment about y by the total mass to find the x coordinate. So it's just x times this same function. To get the moment about y, integrate that, divide by the mass here. So you have to do two integrals and divide to get x bar. The next one, again, is probably better done with functions of two variables, but if we know that the density on each strip only depends on the x value, then the y coordinate of the center of mass for the strip is halfway between the boundary curves, halfway between the two numbers f of x sub k and f of g, and g of x sub k is just the average of those two, f of x sub k plus g of x sub k times 1/2. So the moment about x is just y times f of x minus g of x rho of x, integrated from a to b. But y is 1/2 f of x sub k plus g of x sub k. Which once we take limits, all the sub k's are gone. Now notice we have f plus g times f minus g. This gives us a difference of two squares, f squared minus g squared. And so this is the formula for the moment about x. Divide that by the mass to get y bar. So summarizing our formulas, the mass is top curve, f of x minus bottom curve, g of x, parentheses around that, times rho of x, the density, dx, integrate from A to B. Moment about y is x times f of x minus g of x times rho of x dx. Again, integrating from A to B. The moment about x is 1/2 the integral from A to B of f of x squared minus g of x squared, all in parentheses, times rho of x and then dx. And then, as usual, take m sub y divided by m to get x bar, and take m sub x divided by m to get y bar. Now what we want to do is find the mass, moments, and center of mass of the following planar lamina in the first quadrant of the density at point xy is 5x. See, it doesn't depend on y, just of x. And it's bounded by the curves y equals x to the fourth and y equals 4 to the x, and x is going to go from 2 to 4. So here's what the graph looks like. And notice that the two graphs cross at 216 and at 4, 256. And this is the only part of the first quadrant where the power function is above the exponential. To the right of this, the exponential is definitely going to dominate. So anyway, there's the region. And notice this centroid is just outside the region. The centroid might be in the region or it might be outside of it because of the kind of crescent shape here. Well, not really crescent shape, but anyway, because of the shape of this thing here, the centroid's a little bit outside the region. Now, in the setup that we're getting ready to do to solve this, it is possible to do this exactly using the techniques we've done, but for now I'm just going to set up the appropriate integrals and then approximate them with the technology, graphing calculator. So let's see what we got here. So the mass is just the integral of, think of a vertical strip here, top curve minus bottom curve. Top curve is x to the fourth minus, and then the bottom curve is 4 to the x. The density was 5 times x, and we got dx, and then integrate from x going 2 to 4. The 5 I brought up front, the x I can bring out here, I can distribute or just leave it like this. But anyway, at some point I'm going to put that in a calculator, which is what I did here. And I got an approximate answer of 406.5 and some more. The moment about y is take that same function and just multiply by another x. So we got a 5x here and an x here, gives us a 5x squared. So all I did is I went back here and changed that x to an x squared, and there's the moment. When I found the mass, I stored it as m, so once I have this answer, I divide it by m to get the x bar, about 3.27. Get the moment about the x to be integrating 1/2 times the integral of f of x squared minus g of x squared rho of x. Well, this is x to the 4th squared minus 4x to the squared. Simplify a little bit before I put it in the calculator. Multiply powers here and you get x to the 8th, and multiply the powers here, you get 4 to the 2x. So I think I put it in that form in my calculator. There it is right there. And you get 47,208 decimals. Divide that by m, and I get 116.1262, whatever. So I graph that, and that is the point right there. Notice that the function being 5x for the density is low on the left and bigger as you go on the right, but it's constant on a vertical strip. All right, so hopefully that gave you some idea of what to do with centroids, mass, center of mass, and so forth. All right, time to work some more problems.